Okay, welcome back. So today what we are going to do, we are going to do your surface integral of vector field. Surface integral of vector fields. Okay. So what I'm going to do, firstly, I'm going to tell you what exactly we are heading for. So then I'm going to stop in between. So I'm going to take you back to some concepts which will be required in order to understand the surface integral of vector fields, and then I'll proceed further. Okay, fine. So surface integral of vector fields, what we do, like I said earlier, when we did, the simple, surface integrals. So then what we were doing, we were simply doing something like your f of x, y, z, and then ds, right, over some region s. So basically, what is going to be done here? So now this small f of x, y, z, it is going to be replaced by your dot product of some vector functions. Okay, and those dot product of those vector functions, it is going to again give you a scalar function. So I think the power has gone. What I'll try to do.
The screen has gone black.
Yeah, because the power has gone here, but my computer is still on because it is attached to some UPS. Okay, I think it is visible a bit now, right?
It's fine.
Yeah.
Okay, fine. So now what we will do here, we are going to consider some surface. Okay? Suppose this is the surface S. Okay. So then what we are going to do, we are going to take a point here, say pxyz, and of course this surface, it is in three-dimensional space we are going to consider. Okay. So then at that point, I'm going to consider a outward unit normal, and then suppose I define a vector field F. Over this surface. So basically what I'm going to do, like at all the points in this surface, I'm going to assume that I'm able to define a vector level function. Okay. So then you know that this f dot n cap, that is going to be a scalar. and it is going to be in the form of f of x, y, z. So now what I'm going to do, I'm simply going to find out the integral of this function. So that's what we are going to do. Okay. So now, before moving further, what I would like to do, because you know that what I'm going to do again, I'm going to divide this surface into some patches like this, right? And then at each patch like this, I am going to consider something, right? So basically, at each patch, what I'm going to do, say, suppose this patch, it is denoted by Sij. So what I'm going to do, so basically, I'm going to multiply this function. This is going to be eventually a function of x, y, z, isn't it? And I'm going to take a representative point here. So the value of the function at that point, and then I'm going to multiply it the area of this false patch, and then I'm going to add all those patches. Oh, sorry, I'm going to add this quantity, this expression to be precise, over all those patches, and as the number of patches increases to infinity, that is going to give me the surface integral of the vector level function. That's it. So here, what we are here, you will see that what are the two things that we have. That one is a unit normal 2D surface at that point, and then another thing is that vector level function for which we are seeking the surface integral. Okay. So now let us set this aside. So what I am going to do, I am going to assume that, so suppose this surface is like a net, surface is like a net or a curtain that this is an imaginary net that is in some fluid. Let's suppose it is immersed in some water or something like that, and water is flowing over that imaginary surface. Okay, so then what is going to happen? Say suppose so definitely if I consider this as a surface, say suppose it is some kind of a closed surface. Suppose it is some kind of a closed surface. So then what is going to happen? Like say if you consider that patch, suppose that patch is at the other end. So then obviously, like you would be able to draw some columns like this. You'd be able to draw some columns like this, okay, over this surface. So basically what is going to happen? I mean, the water is going to enter this column, okay, and then it is going to come out of this column from the other side of the surface. Are you getting the point? I mean, if it is something like that. Say suppose I'm considering this as a closed surface. So suppose this surface is nothing but a net that is being immersed in some water. So then what is going to happen? If water is entering through this point, it is going to come out of this point, isn't it? From the other side. So then what you can do, I mean, you can think about an imaginary column like this. Is it okay? That part? Yeah. So, okay. So now let us take you back to, if you recall, your scalar projection. So what we did, suppose I want to take scalar projection of this vector B over another vector A, say, right? So then what we did, that means I simply want its projection over this means I simply want this length. If it is scalar projection, right? If this length is L, so then you know that if this is theta, then L by this B, L by B, this is cos theta, right? So this means your L equal to your B cos theta. Is it okay? Fine. So this I can write as, if say over the vector A, I consider a unit vector A cap. So then the mod of A cap is simply going to be 1. So I can write this as this. So then this is nothing but what? This is nothing but B dot A cap. Is it okay? Yes? Right?
Yes, sir.
So that means, I mean, see, the same thing. I mean, in physics or in other engineering topics, what they are going to do. Suppose you are considering some physical quantity denoted by a vector f. So then, if you want to compute the component of this vector field along some particular direction, if that direction I am calling it say A, so then that component is simply going to be given by f dot A cap, where A is a unit vector along that direction. Okay. Likewise, now let me come back to this situation. Okay. So suppose the fluid is moving with some velocity. Say with some velocity v. Say. Fluid is moving with some velocity v. Here. Okay. And this n cap. This is a unit vector on the small surface like this. patch like this. Okay, so then if I want to compute the component of this velocity along this direction, so that is simply going to be v dot n cap. Is it okay? Just like this.
Yes.
Right? So now see velocity. This is velocity. So this is simply a scalar quantity now. This is the component of velocity. So in class 11, 12, when you studied physics, so distance, if this distance is s, distance by time, this is nothing but velocity. This is nothing but velocity, isn't it? So if I want to find out distance, distance is simply velocity into time. Is it okay? Fine. So that means what is going to happen? I think it is even darker now, right? Can you still see this?
Very big.
Yeah, it is coming back. Okay. So now simply look at this. So now, if you assume that this column, the fluid while entering this column, so suppose it enters here, it comes out through this point on the other side. If delta t is the time taken by the fluid to cross over this column, so then this distance is simply going to be velocity into time. So that is simply going to be given by your v dot n cap into delta t. Is it okay?
Yes, sir.
Fine?
Yeah.
Okay. So now this is the distance. So now see, I have a situation like this. So basically I have a situation like this. I have a situation like this. So this distance is v dot n cap delta t. Okay, and then suppose this is say the area of this patch is say, suppose it is say ds. It is say ds. So then the volume is going to be given by this length into this area. So this volume is going to be given by this into ds. Fine? Okay? And you know that density is nothing but mass per unit volume. Okay? So if you want to find out the mass of the fluid that is inside this column at so for time delta t, so then rho into this is going to give you the mass, isn't it? Right? Is it okay? So that means mass of the fluid contained in this column per unit time is going to be given by this divided by delta t. So it is simply going to be given by this. It is simply going to be given by this. It is simply going to be given by this. Okay. So now, then, if you integrate it over the whole surface S, that is going to give you the mass of the whole fluid there. Okay. So now, so that means if I take this rho v dot n cap ds, this is going to give me the mass of the fluid, right? So that means you can bring an analogy to this. So if I consider rho v to be simply is some vector function f, so this is going to represent something like this. And what does it represent? It is, if you recall, this was nothing but mass of the fluid going across that volume in unit time, isn't it? Because you remember there was some delta t there, only with delta t, I mean, we had the mass. Because we had divided it by delta t, it represents mass per unit time. So whenever you have some quantity moving across something per unit time, that is called the flux. That is called the flux. So let me, go over the slide. I am going to have a better description here. So this is what the surface integral of vector is. So here, what we are doing, we are considering S to be an oriented surface. So what is an oriented surface? For a closed surface, that is a surface that is the boundary of a solid region E. The convention is that the positive orientation is 1 for which the normal vectors point outward from E, and inward pointing normals give the negative orientation. Okay, so you simply consider that paper weight that I showed to you, right? So you can consider that to be what, some solid region E, and it was bounded by that surface S. So it is going to be something like this. So suppose that S is an oriented surface with an unit normal vector N like this, and imagine a fluid with density rho xyz and velocity v xyz flowing through this S. So what I told you, think of S as an imaginary surface that doesn't impede the fluid flow like a fishing net across a stream. Then the rate of flow mass per unit time per unit area is rho v. This I have already told you, right? This I have already told you. So if we divide S into small patches Sij, then Sij is nearly planar, and so we can approximate the mass of fluid per unit time crossing Sij in the direction of the normal N by the quantity this. Okay, where this rho v and N are evaluated at some point on this patch. Okay, by summing these quantities and taking the limit, we get according to definition 1 that I had already done for surface integral. So this you can, that rho v dot N, you can consider it to be a scalar function of variables x, y, z. So over S, and it is simply given by this. It is simply given by this. Okay. So this is what I told you. So volume of fluid crossing ds in delta t second is nothing but volume contained in cylinder of base delta S and slant height v delta t. I have already told you that what is this slant height v delta t? It is nothing but the distance. Okay, right? And what is the role of this n cap? It is going to give you component of velocity along the direction of n. Okay, so that is why volume per second of fluid crossing ds, it becomes this, and so that the mass of fluid crossing ds per second is going to be simply, you have to multiply it by rho. Okay, where rho x y z is the density of the fluid at the point x y z. So this situation is like that, as I have told you. Here, if you consider fluid is coming from that direction to this direction, so this is going to be my situation. Is it okay? Fine. So this is nothing but the definition of your this one. It is coming now. Definition of surface. Okay. So if F is a continuous vector field defined on an oriented surface S with a unit normal vector N, then the surface integral of F over S is given by this. So as I have told you, this integral is also called flux of F across S, because it is something like that mass per unit time. So basically, it is some property, some physical property. Okay, so which is coming across that surface per unit time. Okay, so now we can easily, do some exercises because you already know. And again, remember this ds. Let me. You should not worry about that ds. Okay, so this is this is a vectorial surface. So meaning of this is simply n cap ds. You take a very infinitesimal surface having area ds, you multiply it by the normal on it, so you get the vectorial surface. Okay, so basically your f dot ds, this means f dot n cap ds, f dot n cap ds. This is very straightforward. Okay, and then as you know, you say if I take, so meaning of this is simply f dot n cap ds, f dot n cap ds, and if I consider, as you recall earlier, so what we did, if we consider this surface, if we consider a surface in such a way that any point on that surface, if you join it with the origin, so that vector can be expressed, or that vector can be parameterized with the variable u, comma v. So then you know that your this n cap is given by what? N cap is given by your
RU
RV and divided by
its modulus.
This, and again you know that ds it is simply what? It is simply RU cross RV dA, where this dA is nothing but the original patch that you have considered in the UV plane, if you recall, right? That is the area of that patch, and it doesn't necessarily have to be, rectangular. Okay, so these two will go out, and eventually this is going to be given by this. Okay, so let us try to work out some example. Okay, so find the flux of the vector field. So it is about find the flux of the vector field, your f, it is given by zys. So zi plus z plus xk across the unit sphere, x squared plus y squared plus z squared equal to 1, x squared plus. So here, and again, so flux means what you have to do, you have to simply find out this ds. Okay, here s is the sphere given by this, s is the sphere given by this. Is it okay? So this again, what you can do, you can simply follow that formula. Simply follow that formula. So it is going to be d, then f dot it is going to be this, if you recall.
Spherical polar coordinates.
Yeah, spherical polar coordinates. So, and you know that for this one, because we have already done it, I am going to simply plug them in. So sine square phi cos theta. So it was j and plus, I think it is cos phi Sin phi cos phi k. Sin phi cos phi k. Sin phi cos phi k. Okay. So, and I do it in some other way also. Please don't worry about it. This we have already done. That is why we can write it down. We can write it down. So, and again, you know that x equal to your sin phi cos theta, your y equal to sin phi sin theta, and your z equal to cos phi. Okay, z equal to cos phi. So basically,
Sir,
what
will this be sin phi cos phi or some theta will be there? Below.
below? No, sin phi cos phi. It is sin phi cos phi.
Okay.
Yeah, it is sin phi cos phi. Okay. So from here, what we are going to do. So now what I'm going to do, I'm going to convert it into phi theta. Phi theta. So f is your j. So firstly, I mean you have to take this dot this. So j is cos phi. So you have to multiply this component by cos phi. So I am going to have sin square phi cos phi cos theta. So then y is sin phi sin theta. So I have to multiply it by this. So I am going to have sin cube phi sin square theta, and then this is x sin phi. So sin square phi cos phi sin square phi cos phi cos theta. Okay, so I am going to have this, and then simply d phi d theta, and again your phi is going to be from 0 to pi, theta is going to be 0 to 2 pi. Okay, so now interestingly you can see that, I mean you please, I mean you don't need to worry about this being a big integral. Okay, so it is kind of variable separable type, isn't it? Is it okay? Fine. Each of these individual functions, they are of variable separable type. So for example, this first one, I can simply write it as phi equal to 0 to pi, and then sin square phi cos phi d phi, and then 0 to 2 pi cos theta d theta. Is it okay?
Yes, sir.
Yes.
Right? And you don't even have to worry about it, because cos theta is going to give you sin theta. And when you plug in 0 and 2 pi for theta, this is going to give you 0. So this you can easily neglect, isn't it? Right? Similarly, the third integral also you can neglect. Are you getting my point?
Yeah.
So it's a matter of only evaluating this. This you can easily do. You please try to do it at home. Okay. So I am going to have 3 terms here. Okay, just integrate it, because the first and third, that is going to give you 0. Is it okay? Fine, because you can separate those variables like this. Okay, so you can easily integrate it. So now, interestingly, what I would like to do here, and let me tell you. So I can perform the integral in some other way also. So now see, I mean, this n cap is what? It is nothing but a outer unit normal on the surface of the sphere, isn't it? So the sphere is given by this. Sphere is given by this, right? So I can consider this as a level surface, isn't it? I can consider the equation of the sphere as a level surface, right? And I know.
Same F.
Yes.
Don't use capital F, please. Capital F is the
Oh,
vector.
it is already given. Yes. So let us use pi. Okay. So then a unit normal to this surface, it is simply going to be given by grade phi by mod of grade phi, isn't it?
Yeah.
Okay. So then grade phi, it is simply going to be your 2x, 2y, 2z, and your grade of mod phi, it is simply going to be eventually given by this x square plus y square plus z square, and this is simply 1, x square plus y square plus z square equal to 1. So you are simply going to get x, y, z, isn't it? Fine.
Yes.
So here also you can do the same thing here. Here also, I mean, you can simply like whatever I have done. So like this you can multiply. This you can multiply. I actually eventually your like now it is simply going to be. Let me tell you, it is simply going to be. So that means your zx plus y squared plus xz ds. So basically it is going to be 2zx plus y squared ds. Okay, and then you know how to perform integration. How to perform integration for this one. Okay, because ds is simply going to be your r phi cross r theta dA, right? So then you evaluate this, and then you know this value also, each value also, it is going to be simply sine square phi, I guess, for this. Okay, and then you perform the integration. Is it okay? Fine. So sine square phi or sine phi? Was it sine phi or sine square phi?
I don't remember.
Yeah, but anyway, you can easily work it out. So you can do it through that also. So just let me try to do another interesting one. So you have to find out the same thing, flux of the vector field. Flux of the vector field. Your F equal to same thing, yxj. So it is yxj over the surface S, and this S is nothing but what S does. S encloses the region E, solid region E, I mean, which is enclosed by the paraboloid, your j equal to 1 minus x square minus y square, and the plane j equal to 0. Z equal to 0. So basically, you have to find out your this. You have to find out this, where f is given by whatever I have written in the blackboard, and S is the boundary of the solid region E enclosed by the paraboloid, z equal to 1 minus x square minus y square, and the plane j equal to 0. So, I mean, if we have an idea of the surface that encloses that region E, so our job is done. Okay. So now again, remember, you need to visualize the surface well. Only then you will be able to, I mean, perform the integration. So if you recall, so this parabola, you know, x square plus y square. If you take, it is going to be this parabola, isn't it? So minus of that it is going to be this. So if you raise this 1 unit up, 1 unit up, so you are going to get this paraboloid. Are you getting my point? So this is the paraboloid z equal to 1 minus x squared minus y squared, and then we have to consider z equal to 0. So basically the surface S is given by this surface plus this surface. This is z equal to 0. Are you getting a point? Yes?
Yeah.
So now that means if I want to find out, so this, so if I call this surface as S1 and this surface as S2, so this is simply going to be S1 f dot ds plus S2 f dot ds. Is it okay? Fine. So now, and you know that this is simply what? This is simply this. Okay. Now, firstly, let me concentrate on S2 because that is much easier to evaluate. So now see, over both these surfaces, you have to consider unit outward normal. Okay. So now your S2 is this disk, isn't it? Fine. This disk, and an outward unit normal, it is going to be along this direction, isn't it?
Yeah.
Fine. And this direction is nothing but what? Minus k cap. Is it okay?
Yeah.
Fine. So now you see, if I want to find out f dot n cap, so basically I have to find out what? I have to find out this one. I have to find out the dot product of your yi plus xz plus zk plus zk, right? Dot this
Minus k.
minus k, sorry. Yes, minus k. Is it okay?
Yeah.
Fine. So this is going to give me simply minus zk cap, isn't it? I am simply talking about f dot n cap. Is it okay? Fine. But what is the value of j on this disk?
Sir, the dot product is a scalar.
Yeah. Sorry. Minus z. Sorry. Yes. So what is the value of j on this disk?
0.
0.
0.
Isn't it? So that is why the second component of this integral, it becomes 0. Is it okay? Fine. So let us concentrate only on the first component. Okay. So for the first component, your and again n cap we can easily find out, isn't it? N cap we can easily find out if it is given by the graph of a function. N cap is simply what? Minus j dash minus j y 1, isn't it?
Yeah.
Fine. So in fact this divided by square root
Unit vector.
but let me tell you, just a minute. Let me tell you. Okay. So this part you have already understood. That this is going to be 0. So since here, this surface S1, it is given by the graph of a function of two variables. So if you recall, or I didn't. Okay, let me come to that one. So what is going to happen? So let me. Okay, so if S is given by something like say Z equal to your g of xy. So then what is going to happen? Suppose your f is given by PQR. F is given by PQR. Okay. So then what is going to happen? This ds. So this is going to be your PQR, right? Dot PQR dot, and then this is going to be given by minus zx minus zy 1 divided by, square root of this. Okay. On the other hand, so this is f dot n cap. ds is simply your gx squared gy squared plus 1 dA, isn't it? Fine. So these two will be gone. So then simply what this is going to give you, this is simply going to give you your d. Then this is going to be minus pgx minus qzy plus r dA. That is simply going to be given by that. Is it okay? Fine. So that is why since this is 0, from here we can simply write it as your f was what? F was yxj. So your f was yxj. So and what is minus zx is simply minus 2x, zy equal to minus 2y. So if I use this formula, so then that is going to give me what? 2xy, and then again 2xy. Fine, and then plus z dA over d. Fine. Okay. So then what you do? Simply this one. This is 4xy plus z dA. 4xy plus z dA. So now what is going to happen here? For j, you simply substitute this, okay? And then what is d here? So
this disk.
This d is just this disk. So once you substitute z in terms of x and y, after that you convert it into polar coordinates. You already know how to work it out, right? So you can easily find this out. Okay. So this leads me to find out, and please remember that you if you are given a problem of surface integral of the vectorial function, so you may not be given in terms of something like this. You may not be told to evaluate this, but you will be told to evaluate the flux of the vector field F over the surface S, which will be given by some expression. Then basically you have to evaluate this integral. That's it. Okay. So now let me come to Stokes theorem. Again, in Stokes theorem, we are going to deal with, positively oriented surface. You already know it. So what is a positively oriented surface? you know oriented surface, right? But positively oriented surface, I probably still haven't told you. So oriented surface is just, it has two distinct sides. You'll be able to, at a particular point of the surface, you should be able to draw one outward normal and one inward normal. So that is the definition of a oriented surface. Now, positively oriented surfaces, like say, suppose you are given some surface, and suppose you can enclose it. You can enclose it with some boundary. Say, I can consider a hemisphere. I can consider a hemisphere like this. So then I can enclose the hemisphere with some boundary like this. I can even consider something like this also. Something like this also. Okay? So now if you choose the boundary, in such a way that the surface is always going to be towards your left, then we say that this surface S is a positively oriented surface. And remember, this surface doesn't necessarily have to be a closed surface, although you will come across many problems involving closed surface. Closed region. So, like say, you are going to have like some solid like this. So this is going to be bounded by this surface. This is going to be bounded by this whole surface. Okay, fine. So let me just show you. Let me just run through the slide, and then I'll check it. So basically, the Stokes theorem, what it does, it is again as before. It is going to convert a line integral into a surface integral. Okay. So this is the Stokes theorem. So let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Okay. So basically here they are simply talking about an oriented surface which is piecewise smooth like this S, and then they are talking about say it is bounded by this curve C. So you can see that the direction of the curve is that if a person is walking along the curve, so then the surface is always going to be on your left. Is it okay? Fine. So if F is a vector field whose components have continuous partial derivatives on an open region in R3 that contains S, then you can see this line integral is given by a surface integral. This line integral is given by a surface integral. Okay, so now here I have been given S to be an oriented piecewise. So I am proving this theorem for general surface. It is extremely difficult. So what I am going to do, I will try to prove this. For a surface, which is nothing but the graphql function of two variables. Okay, so that is what I will try to do. So here, what your okay, this is what it does. So if you recall, this one, we have. Do you recall Green's theorem, vector form of Green's theorem? So in vector forms of Green's theorem, if you recall, this was simply F, and then if we take a unit tangent vector, see what we were doing. We were considering what? You have forgotten. Region D bounded by a curve C, right? And what we did, we consider a unit tangent, and then this was the arc length. This d small s is arc length. So this was along what? Tangent, right? Remember, this integral is to be evaluated along the tangential direction. Whereas this is what? This is along the normal direction. I mean, see, if I consider this surface to be a planar surface, if I consider this surface to be a planar surface, okay, so it is not lying, this surface is not lying in 3D space. Suppose I consider this surface to be lying on 2D plane. So then, if you recall what happened to that? What happened to that? This was becoming what? Or this integral was becoming what? If you recall, it became this curl of f, and then this ds was nothing but n cap ds. So in that case, your that unit normal was k, if you recall, isn't it? So it became this. Does it ring a bell? Does it ring a bell? Green's theorem? Vector form of Green's theorem, right? So
I'm unable to get anything.
Yeah, so this thing I did vector form of Green's theorem. Okay,
Oh, yeah.
fine.
Yeah.
So in 2D, so that is why in 2D, this Stokes theorem, so this is nothing but the Stokes theorem. It reduces to Green's theorem. Okay. So as promised, what I'm going to do, I will try to prove this. When your surface S, it is nothing but the graph of a function of two variables, right? Two variables S and Y. Okay. So what we are going to do, okay, suppose this is my surface J equal to something like maybe g of xy, okay, and then so let the projection of this surface over xy plane. Say, suppose it is something like this region D, and let this surface be bounded by this closed curve C, and let the corresponding curve here on xy plane, let it be C1. Let it be C1. The figure is clear, right? So what we are doing, we are considering a surface S here in 3D space in such a way that this is nothing but the graphical function of two variables. Okay, and suppose it is bounded by this curve, this positive oriented curve C, and then we are this surface, because it is the graphical function of two variables, so the domain of this function is simply this D, fine. And then if you take the projection of this curve over here, so then this C is corresponded to C1 on xy plane. Is it okay? Fine. So
Yeah.
that means if this curve C1 it is parameterized by RT. This is equal to xt comma yt, where your t lies between a and b. So then your c in three-dimensional space, it is going to be parameterized by something like your xt yt, then g of xt comma yt, isn't it? Fine. So basically, you take any point, say xy here. So corresponding to this point, if you have x, y, z here, so then your this vector is small r and this vector is capital R. Is it okay?
Yeah.
Right? So this is the way we can parameterize this curve C1 and this curve C. Okay, fine. So now let us, yes. Now this is clear, right? This, in fact, the clue in proving this theorem, it lies here. You don't need to worry about it. If you have understood this, everything is pretty straightforward. You have to just know, I mean, change. You have to just know change. Okay. So okay. So you know the right hand side. You know this is my right hand side. This is my right hand side. So right hand side eventually it is simply S ds. Okay, fine. So now look here. If I consider your, suppose your f is given by simply PQR. So then this is no, sorry. Right hand side is curve f, isn't it?
Yeah, I was confused.
Right hand side is simply this. Right hand side is simply this. Okay. So if f is given by this, so then your curl of f is now del r del y minus del q del z del p del z minus del r del x, then del q del x minus del p del y, right? This one, and then your dot, your n cap is simply minus del z del x minus del z del y, and what? This ultimately I can convert it into this into dA, isn't it?
Yeah.
Fine, this into dA.
Yeah.
That's it. So I love this figure. I don't want to erase it. So this is going to be eventually, and this instead of S, this is going to be D. This is going to be D, isn't it? Right? This is going to be D. Okay. So this is eventually your minus del Z del X, and this del R del Y minus del Q del Z minus del Z del Y del P del Z minus del R del X, and plus simply del Q del X minus del P del Y then dA. That's it. So this is my right hand side. Okay. So now what I'm going to do, I'm going to concentrate on my left hand side. Okay. Fine. So I guess you'll be able to recall this. Even if I erase this, you'll be able to recall this. Or should I keep it like this? Let me keep it like this. Okay, I think I can utilize this. So this was my right hand side. So left hand side it is f dot dr. And yeah, so if I convert it into that in terms of t, in terms of the parameter t, so then you know that this is going to be something like f of rt. So then dot, and this is going to be maybe on the just a minute. Right. Okay, fine. Don't worry about it. I can don't worry about it. Let me r prime t, then dt. I can do it like well, see, I am using capital R because I want to make a distinction between the vector in 2D plane and vector in 3D plane. Okay, so basically, see this capital RT. This is simply your xt, yt, j. That's it. Where again j is a function of, x and y, right? You can again convert it back to the function of t. That's okay. So this is going to give you basically what your p dx dt plus q dy dt plus r dz dt dt, isn't it?
Yeah.
Fine. So now see z is a function of x and y, right? Okay, so that means your dz dt, this is equal to your del z del x dx dt plus del z del y dy dt, isn't it?
Yeah.
I could have used zero also. You know can use as the same. So that is why I can write it as a to b. See, if I replace dz dt by this one, so this is going to give me p plus r del z del x. P plus r del z del x dx dt plus then q plus r your del z del y dy dt and then into dt. Is it okay? Just I'm simply making use of this. Okay?
Okay.
So now what you can do, you can simply remove this dt. You can simply remove this dt. So then I can simply use this as again over c. Is it okay? Fine.
Yeah. Now
So
it is
then-
p dx plus q dy.
Exactly. Exactly. So then if I use Green's theorem, so then this is going to give me, this is Q. So del x of, I mean, Q R dz dy minus del y of P plus R dt. Is it okay? Fine?
Yes.
Okay. So now maybe I have to give a DO to this field.
Now it's a calculation.
Yeah, so next is simple calculation. So now you have to be careful. What I'm going to do, I'm simply going to work out one. So then from here you are simply going to reach this. Okay. So now you have to be careful. So why you should be careful? I'm telling you. See, my first integral. The first thing I have to do is del x of Q plus R del z del y. Remember, both Q and R, they are functions of x, y, z, where z is again a function of x and y. Is it okay? Fine. So that is why say this is going to be what I'm telling you. This is going to be your del q del x plus, and again this is product of two function. It is going to be your del r del x del z del y, and then r del 2z del x del y. Fine. Okay. So now this del q del x, q is a function of x, y, z, again j is a function of x and y. So that is why this is going to be what?
Del q del z del x.
Del q del z
Times del z del x.
del z del x. Are you sure? Just a minute.
It's not correct.
It should be correct, but I'm looking forward to one more term. Just a minute. Did I miss something here? Just a minute. I think we need one more term. Just a minute. Just a minute. Let us not think in this way. Okay, fine. Let us, can we do something like this? Yes. This should be your this. So remember, see, this is in fact something like this. Yes. It is a function of x and y. This is going to be fine. I think this should give me eventually del q del x plus this del q del z into del z del x. Am I correct or not? I should have, because this term, this is del y del x, this is 0. This is simply 1. Right? I should eventually end up with del q, but in that case,
It looks correct.
yeah, it should be this. It should be this. Okay. Yeah, because if I use chain rule, it should give me this. Okay. So from here, I am going to get del q del x plus del q del z del x for this part, and for this part I should get your del r del x plus del r del z del z del x del z del y plus r into del z del x del y. Okay. So now similarly from here also you can get it, and eventually once you simplify that, that is going to give you simply the right hand side. Okay, so that you can easily do. Okay, so in my next class, tomorrow probably, what I'm going to do, I am going to so just before that, let me just show you this one. So this I have already explained. Line integral around the boundary curve S of the tangential component of F is equal to the surface integral of S of the normal component of the curve of F. So this analogy I have already told you. Okay, and this proof I was doing only for situations like this. Okay, fine. So in my next class, I am going to do a couple of exercises for Stokes theorem. And here, one thing, it is very, intriguing. Now, whenever you have, you have a closed surface. You have a completely closed surface. So then, like if you consider a globe, now I can assume this globe to be bounded by this great circle, isn't it? Now I can consider this to be bounded by some small circle also, isn't it? And then if I go on reducing this circle, then I can get a point here. Are you getting the point?
Yeah.
So these kind of concepts, it is going to be very, very important in working out some of the examples, and particularly in physics, they make use of these kind of concepts a lot. Okay. So in my next class, and again in your tutorial sheet, you are going to have enough examples. So then I will see you in my next class.